This is the third lecture of week 10. So in the previous lecture, we talked about how to deal with situation when you have a factor or characteristics that you cannot observe or measure. But the factor doesn't vary over time, but it varies across the state. So one of the examples that we talked about was the particular driving culture in a state. So for instance, driving culture in California and driving culture in Texas can vary, but driving culture in California may not change over time period that we're observing. So in that case, we can use something called fixed effect, or in this case, state fixed effect, to control for this driving culture characteristic that doesn't change over time. In this lecture, we're going to talk about how to deal with characteristics or factor that actually changes over time but doesn't vary across entities or state. So in that case, we can include something called a time fixed effect. And one of the examples of this would be how safe the car is nationally. So because of technological development, the car has gotten safer over time. And this changed over time, but it didn't vary across state. So in this case, we can include something called time fixed effect. And including this term ST, which we call time fixed effect, you will see in the next slide, basically produces different intercepts for different time periods. So it's similar to the state fixed effect that we have seen, but the state fixed effect produces different intercepts for different state, whereas time fixed effect produces different intercept for different time periods. Let's look at a simple model with only time fixed effects. So in the previous example, we had Y, dependent variable, was traffic fatality rate, and X was a beer tax, and S, which is a time fixed effect. And in this case, we can think of this as how safe the car is nationally, which doesn't vary across the state, but changes over time. So in this case, let's say that we want to estimate this model using the 1982 data. So when you plug in observations from 1982, you see that there's some effect, for instance, how safe the car was in 1982, that basically gets observed into the intercepts. So in 1982, you'll have a particular intercept for this model. Let's say that we want to measure the same regression line in 1983. So you plug in different observations from 1983 data, and you see that the new intercept is made up of beta 0 plus beta 3 times this unique time effect from 1983. So basically what the time fixed effect is doing is that it's generating different intercept for different years. So let's look at a more complicated model where we have both the entity fixed effect as well as the time fixed effect. There are multiple ways to estimate this model. In the previous lecture, we talked about when we just had an entity fixed effect, there were two different ways of estimating this. One was demeaning, and the other one was n-1, including n-1 entity indicators. Since here we have two different fixed effects, we have 4 different ways to estimate this in various combination of demeaning and indicators. So we can either have entity demeaning and time indicators, or we can have time demeaning and entity indicators, or we can have both of these time and entity indicators, or both of them using demeaning method. In the data example that we're going to show, we're going to use the first method to estimate the coefficients. So since we are trying to include the time indicator variables, first we need to create all of the time dummies. So the first thing to do in Stata is using generate command to create a time dummies where, for instance, the variable called y83 is equal to 1 when the year is equal to 1983, and otherwise it's equal to 0. And once you create all the time dummies, then you can use the demeaning, you can demean the entity. So the command that we use is xtreg. And in this case, the dependent variable is fatality rate, and the independent variable of interest is beer tax. And then here we're including all of the time dummies or time indicator variables. And then we put this option comma and say tell Stata that we're trying to estimate fixed effect. So this is using the demeaning method for the entity fixed effect, and we're including indicator variables to estimate the time fixed effect. One of the common issue in using a panel data set is that the observation for the same entity are likely correlated. So in that case, we have to use something called clustered standard error. So in the drunk driving example that we have been investigating, it's highly likely that whatever is omitted are correlated over time. So for instance, if the weather condition affects the fatality rate, so how much it snows actually impacts the fatality rate, how much it snows within a particular state is likely to be correlated over time. So for instance, in California, it doesn't really snow year over year, whereas maybe a state like Illinois, it snows a lot every winter. So within state, how much it snows will be correlated over time. So because there is a correlation in unobservable factors, we say that there's an autocorrelation in this case. And when there's an autocorrelation, it doesn't really bias any of the coefficients, but it does affect the size of the standard errors. So when we talked about the cross-section regression, we said that we should use the heteroscedasticity robust standard error no matter what, because this always produces the right standard error, even though there is no heteroscedasticity. Similarly, when you have a panel data, you should use what's called cluster standard error, because when you use cluster standard error, even when there is no correlation in unobservable variable UI within the entity, it's always going to produce the right standard error. So to protect your model against, in case there is autocorrelation, it's always a good practice to use cluster standard error when you have a panel data set. So we mentioned in the previous example that the way to estimate cluster standard error is use the Stata command VCE cluster and the entity that you're clustering. So in our example, we think that there's a correlation within state. So that's why we're clustering at standard error at the state level.